Sheila is investigating the number of square grey tiles needed to make patterns in a sequence. The first three patterns are shown below, and the sequence continues in the same way. In each pattern, the tiles form a square and its two diagonals. There are no tiles in the white areas in the patterns. There are only the grey tiles. In the table below, write the number of tiles needed for each of the first 5 patterns. So let's try to see what's going on for the first pattern. So that is for n equals 1. Well, we see that we have a square of sides 5. We have 5 squares along here and 5 squares up here. So the total number of tiles is 5 multiplied by 5 minus these 4 white squares. So for n equals 1, we have 5 squared minus 4 tiles. So if the entire square was covered in tiles, the number of tiles would be just got by getting the area of this square, multiplying 5 by 5. We have 5 along here and 5 along here, so 5 5s are 25. And then we just subtract 4. So if we work this out, we get 21. I'll just leave it like this just to see if there's a pattern. Now let's look at n equals 2. Well, if there were no tiles removed here, then how many tiles would we have? Well, we just count the number of tiles along the side. We have 1, 2, 3, 4, 5, 6, 7 tiles along one side of it, and because it's square, there's 7 along the other side. So if no tiles were removed, we would have 7 times 7, or 7 square tiles. That's 49. However, we have tiles removed. So what's removed? Well, these 4, which correspond to these 4 here actually. But not only that, we have more new tiles removed here. So we have 7 squared minus the 4 that were removed initially. Those are the ones that I've marked in red. But we have also these new ones removed, which I've marked in green. So these green spaces, how many of them are there? Well, we have 3 of them here, and that 3 is repeated. It actually appears 4 times. So we have 3 times 4. That has to be subtracted from 49 as well. So we have to subtract these 4 ones here with the red dots in them, and the 4 by 3 are 12 squares with green dots in them. So we will get 49 minus 4, which is 45, minus 12, which is 33. Okay, so we're just interested in looking at the pattern first. So I won't write down the actual values. The values are written down here. Let's look at n equals 3. So I'm looking at the third pattern. Now, if we had nothing, if everything was consisted of tiles in this square, then how many tiles would we have? So we just count the tiles along one side. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's 9. We have 9 along here. We have 9 down here. So if all of this region was filled with tiles, we would have 9 times 9 is 81 tiles. 9 times 9 is 9 squared. Now we subtract off the same sort of tiles we subtracted before. We have 4 of them here. We subtract these ones off. So we have 3 down here, and we have 4 times 3. It's the same as this up here. But now we have these new spaces which I've indicated with yellow dots. We have 5 here, and that 5 is repeated 4 times. So we have 4 times 5, which is 20. Now, let's continue extrapolating this pattern. Notice here this is 5 squared, this is 7 squared, this is 9 squared. So the first term for an expression for n equals 4 is going to be 11 squared. Then we will have minus 4, then minus 4 times 3, then minus 4 times 5. Same as this here, but we're going to be subtracting out now another set which will be minus 4 by 7. So for n equals 4, which I'm not going to draw, we would see spaces, the same spaces as for n equals 3. That's the 4 red dots, the 4 by 3 are the 12 green dots, and the 4 by 5, which is the 20 yellow dots. But we'll see an extra 28 dots, and the sides of the square will be 11. The sides of the square are increasing by 2. Okay, now if we calculate this, I think we should get 45 plus 12, because it looks like we're getting an arithmetic sequence here: 21, 33, 45. An arithmetic sequence whose difference is 12. 12 plus 21 is 33. 33 plus 12 is 45. 45 plus 12 is 57. Let's just check that. We have 11 squared minus 4 minus 4 threes are 12 minus 4 fives are 20 minus 4 sevens are 28. Yeah. If we wanted to, we could write out an expression for n equals 5, which is the number of tiles in the fifth pattern. But and we could calculate it, but as you can see, it's much easier just to add 12 onto 57. You might say, how do I know for sure that this is an arithmetic sequence? We've only looked at the first few terms. How do we know it's going to continue in that vein? Well, that would involve analyzing each of these sequences here, which I won't bother doing. At this level, you're either going to expect an arithmetic or a geometric sequence. So, after you've worked out a few values, you can see if it's arithmetic or geometric. It's arithmetic in this case because 33 minus 21, which is 12, equals 45 minus 33. We want to find in terms of n a formula that gives the number of tiles needed to make the nth pattern. So we need 21 tiles for the first pattern. So that's T1 of our sequence. T1 is the first term. We need 33 tiles for the second pattern, this pattern here. So that's T2 of our sequence. T3 is the number of tiles for the third pattern, which is 45, and so on. So we want to find out what Tn is. Now, in a previous video, I derived a formula for giving you the nth term of an arithmetic sequence. The nth term is a plus n minus 1 times d. It's actually quite easy to derive. We just have to apply it here. So a is the first term. A is 21. And d is the common difference. That's the difference that's common to all pairs of consecutive terms. It's 12. So we plug 21 in for a and 12 in for d, and we simplify this to get an expression for Tn, or a formula for Tn. So multiplying 12 by n here gives us 12n. I'll write that term first. As for the constant term, we have plus 21 minus 12. Plus 21 minus 12 is 9. Now if you want to check this, you could just work out T1. Plug 1 in for n. We get 12 times 1 is 12. 12 plus 9 is indeed 21, so T1 is 21. If we plug 2 in for n, we get 12 twos are 24. 24 plus 9 is indeed 33, and so on. Using your formula or otherwise, find the number of tiles in the 10th pattern. So I could write out 10 of these here. That would be the other way of doing it. Just write out 10 terms, just keep adding 12 on each time. Or I could plug 12 into this formula here. So we get T12. It's the 12th term, which is the number of, or sorry, not 12, but 10. We want the 10th pattern. So T10 is 12 times 10 plus 9. That's 120 plus 9, which is 129 tiles. Here is the other way of doing it. Just write out the first 10 terms. And this is T10. Sheila has 399 tiles. What is the biggest pattern in the sequence that she can make? Let's put Tn equal to 399. Now, if we solve this for n, we get n equals 32 and 6/12. So what does this mean? Well, it means she can make the 32nd pattern with 6 tiles remaining. See, the remainder is actually 6. 12 times 32 plus 9 will actually give us 393, but we have 399 tiles, so there's actually 6 left over. So the question is, how big is the 32nd pattern? Well, the first pattern has sides of 5 tiles. The second pattern has a side of 7 tiles. The third pattern has a side of 9 tiles. So you can see that the side increases by 2 tiles each time. As we increase the number of patterns by 1, the sides increase by 2 tiles. So if we want the side of the 32nd pattern, we would have to look at this sequence here. So it's 5, 7, 9, 11, 13, 15, and so on. It's an arithmetic sequence. The first term is 5. The common difference is 2. To get the 32nd pattern, we use the formula a plus n minus 1 times d. We're just getting the 32nd term of this sequence. If you want to get the length of the side of the 32nd pattern. Now I'm not sure if we have to actually do that for this question, but if you want to see what it is, we just see that the sides follow an arithmetic sequence with a equals 5, d equals 2, and we want the 32nd one. So we just use the formula a plus n minus 1 times d with n equals 32. So our pattern would be a square of side 67, 67 by 67. Find in terms of n a formula for the total number of tiles in the first n patterns. Well, that means we must just add all these numbers up as far as the nth pattern, which we know is 12n plus 9. Tn of the sequence is 12n plus 9. So n is any number. Here I've shown a situation where n is actually bigger than 3. I've written down the number of tiles for the first 3 patterns. So Sn just means T1 plus T2 plus T3 up as far as Tn. Here is a formula for Sn, the sum of the first n terms of an arithmetic series. Now this is proved in an earlier video. We'll just apply it here. So we're looking at Sn, so we're not plugging anything in for n. We're getting a formula for Sn. What we need to do is plug 21 in for A and 12 in for D. So working this out, we get 2 times 21 is 42. Here we get 12n minus 12. 42 minus 12 is 30. So we have 12n plus 30 in here, and we have to divide by 2. So, we can just take the 12n plus 30 and divide by 2. And we have n multiplied by 12n divided by 2 is 6n. And 30 divided by 2 is 15. And if you like, you can multiply n into this to get 6n squared plus 15n. Let's do a quick check. Let's check it for n equals 2. S2 should equal 21 plus 33. That's 54. And if we plug 2 in here, we have 6 times 2 squared plus 15 times 2. So we have 6 fours are 24, plus 15 times 2 is 30, and that does indeed equal 54. So it checks out for n equals 2. And it's true for all values of n actually. There's nothing special about 2. I could have picked any number. If it works for any number, the chances are it works for all of them. Sheila starts at the beginning of the sequence and makes as many of the patterns as she can. She does not break up the earlier patterns to make the new ones. For example, after making the first 2 patterns, she has used up 54 tiles. So she needs 21 tiles for the first pattern, 33 tiles for the second pattern. So after she makes 2 patterns, that means 54 tiles are used up. How many patterns can she make in total with her 399 titles? So we're looking at sums of terms of this series here, and we want to see how many terms can we take such that the sum is equal to the total number of tiles that she has to make patterns with, which is 399. So in this case we put Sn equal to 399. That will tell us how many terms of this series we can take, which means how many patterns she can make. Now we need to solve this equation here. But this equation involves n squared, so it's a quadratic equation. To solve a quadratic equation, we get it into standard form. That is, we get 0 on one side. And then you can apply your formula to this quadratic equation here. You can say a is equal to 6, b is equal to plus 15, c is equal to minus 399. If you like, you can simplify it before you apply your formula. You can actually divide all of this by 3. 6 divided by 3 is 2, 15 divided by 3 is 5, 399 divided by 3 is 133, 0 divided by 3 is 0. So we could try to solve this. So a is 2, b is 5, c is minus 133. The solutions are given by minus b, which is minus 5, plus or minus the square root of b squared minus 4ac. That's 5 squared minus 4 times 2 times minus 133. All of this is divided by 2 times a, where a is 2. So you go to your calculator and put in the discriminant of the quadratic equation. That's the b squared minus 4ac. So we have 5 squared, which is 25, minus 4 times 2, which is 8, multiplied by minus 133. So for that, we get 1089. Now we want to get the square root of this number, so a quick way to do that is just to put it to the power of 0.5. That's 33. So we have minus 5 plus or minus 33 divided by 2 2s are 4. So we get two values of n depending on whether we take plus or minus. Let's take plus. So we have minus 5 plus 33 is 28. 28 divided by 4 is 7. So n equals 7. So that means that if we take 7 terms of this series, we will actually get exactly 399. So that means that she can make 7 patterns. So the answer is 7 patterns. Now there is another value of n that will satisfy this quadratic equation. That value of n is got by taking the minus sign. So we'd have minus 5 minus 33, which is minus 38 divided by 4. But that's going to give us a negative value for n, which doesn't make any sense in this context. N has to be a positive number. N stands for the number of patterns. Another way we could have found this is to just simply start adding terms. We just keep adding terms until we get to 399. Turns out that we get exactly 399 if we add the first 7 terms. So I've written out the first 7 terms of this series.